Hey, welcome to the Explainer. So today we're going to tackle a really foundational tool in data science, multiple linear regression. We're going to build it from the ground up so you really get a feel for how it works.
All right, let's start with a really basic question. Just think about, well, pretty much anything in the real world. What causes a student's final grade to be what it is? Or what drives a company's sales? It's never, ever just one thing, is it? The world is just way more complicated than that.
So you've probably heard of simple regression, right? It's awesome for looking at a one-to-one thing, like more study hours equals a better grade. But like we just said, reality is so much messier. A student's grade also depends on their GPA coming in, whether they actually show up to class, all sorts of things. And that's where multiple linear regression comes in. It's the tool built for exactly this scenario, letting us look at how a whole bunch of causes lead to one single effect.
And this is what it looks like under the hood. This is the core equation. We're not just dealing with one x variable anymore. We've got a whole bunch of them, and each one gets its own coefficient. Now, what this means is we're not just drawing a simple line on a 2D graph. You have to kind of picture it in your head. We're fitting a flat plane or even a more complex surface through a big cloud of data points in 3D or even more dimensions. This regression surface is just a much richer way to see all these relationships at once.
And this is the real magic of multiple regression. Each one of those coefficients, those betas, is what we call a partial coefficient. What does that mean? It tells you the unique, isolated effect of one variable while we mathematically hold all the other variables perfectly still. It lets us ask, what's the impact of just study hours completely separate from attendance or GPA? It is an absolute game changer for analysis.
Okay, so we've got the blueprint for our model. We know what it's supposed to look like, but how do we actually find the numbers? The best possible coefficients to plug in and bring this thing to life.
Yeah, this is the big question, right? We've got the framework, but we need the raw materials. We need a rock-solid method to find the values for our coefficients that make the model hug our data as tightly as possible.
And that method has a name, ordinary least squares, or just OLS. Now, the name sounds super technical, I know, but the idea behind it is actually beautiful and simple. The rule is this: we need to find the one regression surface that makes the total amount of error between our model's predictions and the actual real-world data points as small as humanly possible.
And you can see exactly what I mean right here. Each of those little red lines, that's the error. It's called a residual. It's the gap between a real data point and where our model predicted it would be. OLS is the process of finding the one and only line, or plane, where if you square all those red lines and add them all up, that final number is as tiny as it can possibly get. That's the best fit.
Now, you could try to write out an equation for every single data point, but imagine you have thousands or millions of them. It's just no way. It's completely impossible. So, to handle this like grown-ups, we switched to a much more powerful and honestly more beautiful language, matrix algebra.
See, with matrices, we can take that whole gigantic system of equations and shrink it down to this one clean statement: y equals x beta plus epsilon. And as you can see in the table, y is just a big column of all our outcomes. X is our design matrix. That's just a fancy grid holding all of our predictor data. Beta, that's the column of coefficients we're hunting for. And epsilon is what's left over, the errors. It's the whole shebang right there in one tidy package.
And this is the reward for all that setup. With matrix algebra, we get this single, incredibly powerful formula. This right here is the OLS estimator. You just plug in your data, your x and y matrices, and this equation it calculates the vector of best fit coefficients for you. This is the engine room of linear regression.
All right, so we've got a formula. We have a way to get our estimates. But that immediately leads to the next big question. Are they any good? I mean, why should we actually trust the numbers that this formula spits out?
This is like the quality control department. Just because a machine gives you an answer doesn't mean it's the right one or even a good one. We have to ask, does the OLS method produce estimates that are statistically sound? Are they reliable?
Well, it turns out that as long as a few key assumptions are met, OLS estimators have some absolutely fantastic properties. They're linear, which just means they're simple to work with. They're unbiased, which means they're accurate on average. And they have minimum variance, which means out of all the estimators of their type, they are the most precise. They're the sharpest tool in the box.
Let's zoom in on unbiasedness, because this is so important. It doesn't mean that the estimate from your one sample is going to be perfect. Of course not.
But what it does mean is that if you could repeat your experiment 1,000 times, take 1,000 different samples, and run 1,000 regressions, the average of all your estimated coefficients would land exactly spot on the true value. It's like a dart player who, on average, hits the bullseye. There's no systematic bias pulling them to one side.
And look, this isn't just some nice idea we hope is true. It's mathematically provable. You can literally start with that OLS formula, plug in the true model for y, and after a few steps of algebra, you can see it right here. You prove that the expected value of our estimator is the true beta. The whole thing rests on a crucial assumption, though, that our errors average out to 0.
So here's the bottom line. When those important background assumptions are met, a super famous result called the Gauss-Markov theorem proves that OLS is blue. That stands for the best, linear, unbiased estimator. It's not just good, it's the gold standard. You literally can't find another linear, unbiased estimator that's more precise.
Okay, we've built the model. We trust the individual coefficients. The very last step is to step back and give the whole thing a performance review. As a complete package, how well does our model actually explain the thing we're trying to understand? And for that job, we've got two main tools, and they tell us slightly different things. First, there's R-squared. That answers the question, how much of the story does our model tell? Then there's the F-test. That answers a different question. Is the story our model is telling even statistically valid, or could it just be a random fluke?
R-squared is awesome because it's so easy to understand. It's just a score from 0 to 1, or you can think of it as 0% to 100%. So if you get an R-squared of, say, 0.75, that literally means your model explains 75% of the variation in whatever you're measuring. Simple as that. Higher is usually better.
The F-test, on the other hand, is our formal stamp of approval. What it does is it puts our model into a cage match against a totally useless model, one with no predictors at all. If we get a significant F-test, it means our model won the fight. It provides a statistically better explanation than just random noise. It confirms that our variables, all taken together, have real explanatory power. All right, let's wrap this all up. Let's recap the whole journey. What's the story of the model we just built, from the very beginning to the very end? We started with a challenge. The world is complex, so a simple line won't cut it. We picked our tool for the job, multiple linear regression. We used OLS as the blueprint to get the best fitting parameters. We got a quality guarantee from the Gauss-Markov theorem, telling us our method is blue. And finally, we gave it a performance review with R-squared and the F-test to see how well it actually did.
So, we've gone through the mechanics, the how-to of building a pretty powerful statistical model. But the final takeaway I want to leave you with is a question. You now know how to build a model, but the real skill, the real science, is making sure the story it tells is true. Are your assumptions met? Is your data clean? Are you interpreting it correctly? That's the real challenge. Thanks for joining me.